Okay, so we're live on YouTube. I'll just set the security settings the way I like. Okay, that's done. Now I guess I'll start the recording. So if you don't want to be recorded, then video off, audio off. And okay, so so maybe I'll slowly get started. Just before I begin with the math, a brief kind of administrative note. So if you can, please whitelist. So I've sent some messages from this email address, and at least a couple of participants haven't received them. So it would be good for you either to make a habit of checking your spam folder if you're not getting my messages, or to check if you're getting my messages from summerschool@math.quebec, or set a filter to make sure the messages from that address don't go to spam.
Should you be sharing your screen?
I should be sharing my screen. I thought I was. Thanks. So let me do that. I've just written down the address I wish you to whitelist, or check your spam folder for messages from. There it is, summerschool@math.quebec. Great. So as before, please feel free to ask questions. I'll do my best to monitor the chat, and feel free to answer one another's questions in the chat as well if you have a quick response and I haven't noticed the question, which does happen. So I'm going to continue today with looking at uniformly random trees. So let me remind you that so last lecture we saw Cayley's formula, which said that the number of rooted trees with vertex set 1 up to n was n to the n minus 1. I sort of noticed, I don't think this got me in trouble yesterday, but a potential issue with my notation. So I'm going to try to I'd written v of t, if you'll recall, for the sequence, so that we had this bijection between the set Tn and the set of sequences v1 up to vn minus 1, where each term vi is an integer from 1 up to n. Okay, so that and under that bijection, I'd written v of t for the sequence that of integers v1 up to vn minus 1 that's obtained from the tree t. Okay, so separately, I'll write little v of t for the vertex set of the tree t, or more generally, v of t, little v of t for the vertex set of a graph, or little v of g for the vertex set of a graph, and e of t for the edge set of that tree. And so similarly for a graph G, we'll write v of g and e of g for the vertex set and edge set. Okay. So after we proved this via this line breaking construction, we deduced some probabilistic corollaries, including information about the degree of a typical node, and the distance to a typical leaf. Okay, so today I want to continue investigating the probabilistic corollaries by looking at aspects of the local structure of uniformly random trees. And so I'll mean two kinds of things by that, and we'll use one of those things to get at the second one, in fact. So the first thing we'll mean is the subtree rooted at a typical point. Okay, so the picture here is, you imagine that you have this large random tree Tn. This is its root. So we're going to just pick a random vertex of the tree and look up and ask, what sort of tree are we likely to see? Okay, so that's one thing we might mean by a local structure. And the other thing that I'll mean is the local structure near the root. Okay, so from this perspective, you imagine that you're going to, take a magnifying glass. We saw that in this tree, the sort of typical distance, the distance to a typical leaf was like of order root n. But now, when I say local structure, I mean I'm really going to zoom in around the root vertex of the tree and ask about what kind of tree I'm likely to see nearby. Okay, so if n is large, then I expect to see some very long paths going off into the distance. But if I only look out to distance 100 and ask what sort of trees I'm likely to see, then maybe I can hope for sort of limiting statistics, and that's what point B is about. Okay, so to start to get at these, I want to give myself some notation first. So we'll start with A, the subtree rooted at a typical point, and let me give myself some notation for that. So if I'm given a tree T, and my trees are always rooted unless I say otherwise, and a vertex of the tree, then I'll write TV up arrow for the subtree of T that's rooted at V. Okay, and so we can immediately describe the distribution of this using the tools we already have at our disposal. So when this tree T is a large uniformly random tree. So we'll let capital T be the large random tree. Okay, and then for any node of that tree and any integer for k from 1 to n, the probability that the subtree rooted at V has size k is given by the following expression. So k to the k minus 1 over k factorial, 1 minus k over n to the n minus k, times n following factorial k over n to the k. Okay, so this this notation here, n following factorial k, just means n factorial over k factorial over n minus k factorial by definition. But you can also write that as n minus 1, n minus 2, and so on down to n minus k plus 1. Okay. Right. So is this statement of the proposition clear? So we have some combinatorial formula on the right, and I'd like to justify that to you now. One thing I'll note right off the bat is that if k equals n, then the right-hand side gives 1 over n. Okay, so if you take 0 to the 0 equals 1, then this gives a 1 over n. This becomes a n factorial, which cancels this n factorial, and then here we have n to the n minus 1 divided by n to the n. Okay, so and that's indeed correct. So if we take a tree with n vertices and ask for the probability that when we pick a random node, its subtree has size k, well, that subtree has size n if and only if we've actually picked the root of the whole tree. Okay, so that has probability 1 over n because there's only one node we can pick for that to be true, and there's n nodes in total that are possible. Someone asked, what does NB stand for? Yeah, it does indeed stand for nota bene, and it means like important or note. Right. So this is correct, and so when I'm proving the proposition, I can focus on k strictly less than n. That's just so that I think at some point I didn't want to worry about dividing by 0 or something like that. Okay, so is the statement to the proposition clear? Okay, great. So let me continue. So the way I'm going to approach this is very combinatorial. I'll just do some more counting, and I'm going to count the size of the set of trees in Tn with the property that the subtree rooted at this particular vertex v. Remember, we're interested in the probability that the subtree rooted at a particular vertex has size k. So let's just count how many ways there are for that to happen. Okay, because with that definition, then the probability that this random subtree has size k, that's just the size of this set Tnvk, right? That's the number of possibilities. That's the number of ways there are for us to sort of build a tree where this particular vertex v has k nodes in its k vertices in its subtree, divided by all of the possible trees. Okay, and so that's just the size of Tnvk divided by n to the n minus 1. We already know what the denominator is. Okay, so if we can work out the numerator and see that the numerator gives us this expression, then we've proved the proposition. Okay, so how can we count this set? Well, let's just give ourselves an explicit description of an element of this set. So if we want to describe some tree T in this set, I can do it in the following way. So I'm going to think about splitting the tree into two parts. There's So here's the whole big tree. There's one part which is this part Tn TV up arrow, the subtree root at V, and then there's the rest of the tree over here, which is, let me call it T minus TV up arrow. Okay, that's all of the rest of the tree. Okay, so how can I build such a tree? Well, first I'm gonna choose which vertices go in this subtree. So choose the vertex set of TV up arrow. Okay. Second step, once I've chosen what vertices I'm going to build that subtree with, I'll actually build the subtree. So I'll choose the tree, not just its vertex set, but now choose the tree TV up arrow. Okay. And then the third step is to choose the other tree, T minus TV up arrow. I don't need to choose its vertex set because it's just all the remaining vertices. So choose the tree T minus TV up arrow. And fourth, so if I know this tree and I know this tree, then all that remains to decide is where this vertex, the root vertex V, is attached into the brown tree T minus TV here. So that's choosing the parent of V in T minus TV up arrow. Okay, so how many choices are there at each step? Okay, remember we're trying to build a tree where this subtree has size exactly k. We know one of the vertices of this subtree is V, and we have to choose another k minus 1 vertices to go in that subtree. Okay, so the number of possibilities for choosing that vertex set is of those of the remaining n minus 1 vertices, we have to choose k minus 1 to go in here. Okay. Once we've chosen them, then now what do we, in step 2, we're supposed to build a tree with this particular vertex set. So we know how to count those. We're counting the number of rooted trees with k vertices, except the root isn't arbitrary. The setting enforces that the root is this particular vertex V. So the answer, if we could choose any root, would be k to the k minus 1. That's Cayley's formula. But because the root is determined for us, we lose a factor k, and we only have k to the k minus 2 choices. Okay, then in the third step, having chosen that tree, we get to build the brown tree, the tree that's out here. So it has n minus k vertices, and now the root is not specified for the brown tree. We can choose whichever root we want. It's n minus k to the n minus k minus 1. Okay. So here I'm actually using that k is not n, right? This subtree here has less than n vertices, which means that this brown tree is non-empty. It has a root. And finally, once I've chosen the brown tree, then I can choose what this point of attachment here is, and that could be any vertex in the brown tree. So there's n minus k possibilities. Okay, so if I just put all that together, you see at each step, the number of choices didn't depend on what decision was made in the step before. So that means the total number of choices is just the product of these terms. Okay, and that procedure builds any tree in TNVK for us. So the answer is n minus 1, choose k minus 1, k to the k minus 2, n minus k, and now I have n minus k minus 1 plus another power of 1 here gives n minus k. Okay, and I said that the probability I'm interested in computing is the ratio of that and n to the n minus 1. So let's do that. We want to divide through by n to the n minus 1. And then if we gather terms, we can rewrite this as 1 over n to the n minus 1. So n minus 1, choose k minus 1 is n minus 1 following factorial k minus 1 over k minus 1 factorial. Okay, then we still have k to the k minus 2 n minus k to the n minus k. Okay, and so to let's look back at how I'd written the expression. We sort of had the factors of k, then a ratio of terms involving n, and this is n minus k over n to the n minus k. So let's just check that all checks out. If I multiply and divide by k, I get a k factorial on the bottom and a k to the k minus 1 on the top. Okay, and then here I have n minus k over n to the n minus k if I multiply and divide by n. And that gives me an n to the k left over, so I have n minus k over n to n minus k, and what's left is n minus 1 falling factorial k minus 1 over n to the k minus 1. And now, just in the last term, I can again multiply and divide by n to get an n falling factorial k over n to the k. Okay, so that's a pretty straightforward combinatorial proof of this formula for the size of the subtree rooted at a random vertex. Okay, so once again, if you like, there are further combinatorial consequences of the construction. This is really, so I'm going to call these corollaries. They're not quite corollaries in the sense that they don't follow from the proposition as it's stated, but they follow from thinking about the proof of the proposition. So one is that if we look at the brown tree, at the tree we get when we remove the subtree rooted at a uniformly random vertex, then it's again uniformly random, conditional on its vertex set. And the second is that the subtree rooted at that vertex v is also uniformly random. But it's a uniformly random tree. It's a little bit different because we specify its root. So rooted at v and also conditional on its vertex set. Okay, and so the proof of this, so to see that this is true, what you really want to do is think about if rather than so if we're interested in saying that that this brown tree here is uniformly random once I tell you its vertex set, you just say, well, if I insist on seeing a particular tree out here, what does that do to the number of possibilities? Well, it just says that rather than choosing an arbitrary tree here, which gave us this combinatorial factor, now I have a factor 1 because I'm insisting on what tree I see. Okay, but the number of, so that cuts down the number of possibilities by this factor. But the factor doesn't depend on the tree. It's the same whatever tree out here I insist on with that vertex set. Okay, so the number of possibilities in this construction procedure where I decide instead of picking an arbitrary tree at step 3, but to fix a particular tree at step 3 is always the same. And so then the distribution must be uniform over all the possibilities. Okay, so so that's saying in step 3, if I fix the tree t minus tv up arrow, that just removes a factor n minus k to the n minus k minus 1. Okay, and similarly, in step 2, if I fix the tree tv up arrow, that just removes a factor k to the k minus 2 from the number of possibilities. Okay, so the key point is that neither of these factors depend on the precise tree, but only on its size. So there's a question from Hao Chan in the chat, which is whether the randomness is only in the choice of tree, not in the choice of V. So that that is the way I've stated the proposition. This is for a fixed vertex, and then the tree is chosen randomly. So you can think of this as being the vertex with label 1 if you like. Okay, but by the symmetry of the model, it would be equivalent if I let V be a uniformly random vertex, or indeed V to be any distribution over the vertices as long as the distribution doesn't depend on the tree. Because this formula doesn't depend on what V is. So if I put some randomness in the label V, then I'll just be averaging over a formula which is constant. So I'll get the same result out the other side. Okay. So there's a first set of consequences of this proposition and its proof. Another one we get by thinking about the asymptotics of this formula for n large. Okay, well, there's only one term where there's something interesting going on, right? If I think about fixing k, then this and letting n tend to infinity, then here we have a ratio of terms on the top and the bottom that are essentially equal, right? So this ratio will tend to 1. And here we have something which looks like an approximation of an exponential, right? For fixed k as n tends to infinity, this looks like e to the minus k. Okay, and so what that tells us, this really is a corollary of the statement rather than of the proof, is that for fixed k as n tends to infinity, so for any v in n, or if you like, uniformly over vertices of the tree, the probability that this subtree has size k is, so that's the same as if we just look at vertex 1, and that's 1 plus little o 1 k to the k minus 1 e to the minus k over k factorial. Okay. And again, that's just because the exact formula for this is this here, and this tends to 1, and this tends to e to the minus k. Okay, so this is an expression. The expression on the right here is a discrete probability distribution that you may or may not have seen before. It comes up in queuing theory and in the study of random trees. So I'll define it for you. So this is called the Borel or Borel-1 distribution. So the 1 is a hint that it's in fact a parameterized family of distributions. So this is the probability distribution on non-negative integers, defined by, so mu of k is precisely the expression we had above, k to the k minus 1, e to the minus k over k factorial. Okay, and then in this language, the second corollary, let me give that a 2 here. So this corollary 2 says that the size of this subtree rooted at a random node converges in distribution to a Borel-1 random variable as n tends to infinity. Okay, and now there's something that I'm glossing a tiny bit here, and I'll continue to gloss it for a while. But that's So what have we just shown? We've shown that if you take a large random tree and you look at this subtree rooted at a fixed node, then for any particular value k, the probability you see a subtree of size k converges to some value, this value here, okay? But saying that that yields convergence in distribution is also asserting that these values sum to 1, okay? Because we need to be getting a probability at the far side to have convergence in distribution. Okay, so I'll maybe, again, use that nota bene shorthand. So this convergence in distribution assumes that the sum of k to the k minus 1 e to the minus k on k factorial over k at least 0, that's a bit hard to read, sorry, is equal to 1. And that's not an obvious fact. Okay, so I'll invite you to think about proving that. We'll see a proof a little bit later in the course. But I don't know a sort of, I don't know a proof that doesn't involve a little bit of thought for that and some ideas. Okay, but that is indeed a fact. And so one thing that tells us is that if I pick a random vertex in this tree, then the subtree rooted at that vertex remains bounded. So there's a question about that. Yeah, so is there a way to understand why the size stays order 1? Well, I mean, if you like, we've just proved it, modulo this fact that this is a probability distribution. Beyond that, you know, it isn't a completely obvious fact. There are, you know, if we took a tree which was just a long skinny path, then picking a random node, you know, would yield a subtree of size of order n. Typically, it would be a constant proportion of the vertices that are above the tree. On the other hand, if we take, say, a complete binary tree and pick a random vertex, then with high probability, the subtree above the vertex that we pick will have size order 1. Most of the vertices are very close to the leaves. Okay, I mean, one way to see why the size stays order 1 is we can say, once we have a sort of more probabilistic perspective on this and start to think of these as conditioned branching processes, and then then this fact will be related to the fact that critical branching processes go extinct, the fact that the size is of order 1. But we can't quite, I don't quite have the language for that yet. Omer pointed out to me that my sum here should start from 1, which is true. Thank you. Question, why does this argument assume mu is a probability distribution? The argument doesn't require that that mu is a probability distribution. The assertion that this is convergence and this is a convergence and distribution result says that on the right we have a probability distribution. In general, otherwise this would be called like a weak star convergence or something like that. A convergence where, so for every fixed value you have the convergence, but there's some sort of there's some loss of mass, if you like. There's some possibility that the tree has size larger than a constant. Yeah. But no, so what I proved doesn't require, up to this point that I'm showing now on the slides, doesn't require any convergence, anything about the fact that these values sum to 1. It's only in order to call this convergence and distribution. Okay, so as I'm going to state a couple of exercises now, which I'll leave to those who are interested or are doing the group work. Hopefully both. So one is to extend this statement to a joint distributional approximation for the subtree is rooted at more than one vertex. Okay, so this says that for any fixed number k, I guess I want k at least 1, in fact. As n tends to infinity, if I look at the joint, the vector which lists the subtrees rooted at vertex 1 and the subtree rooted at vertex 2, and so on up to vertex k, okay, that the sizes of those subtrees converge jointly in distribution to a vector of independent Borel random variables. So B1 up to Bk are independent and Borel 1 distributed. Right. So the idea is, so in the chat, Lior has sort of got the idea of the exercise. Those who don't, you don't have to feel bad. Lior is a professor, so he has lots of practice thinking about things like this really quickly. Hi, Lior. So the idea for this is to extend. No, I approve of. You don't need to apologize. I approve of the comments. It's helpful because it's actually exactly what I was about to say. So you need to extend the above proof. Okay, thinking about these steps, and the issue is precisely what Leo has put his finger on. So you'll need to show that you can think of maybe doing this inductively. The probability that the vertex with label k is in one of the first k minus 1 subtrees tends to 0. Okay, because if this didn't happen, if vertex k was likely to be in one of the preceding subtrees, then obviously their sizes couldn't be independent. One would have to be bigger than the other. Right. Okay, and so a second exercise before I then this seems like a natural spot for a 3-minute break. I'll state a second exercise. So this relates to inserting. So I'm using vertices with labels 1 up to k as sort of in order to make a statement that where there's no sort of arbitrary choice of v here. But like I said before, how you can also insert randomness over the vertices, that will be useful in a minute. So I'm going to outsource that a little bit to you, but this exercise should be plausible. So if I let L be the smallest labeled leaf of a random tree T, okay, then I want you to show that for any fixed vertex u and n, the probability that the smallest labeled leaf is in the subtree rooted at u tends to 0 as n tends to infinity. Okay. Remember, in our bijection, the smallest labeled leaf plays a special role. So that's why this is going to come up. But because this is true for an arbitrary vertex u, it also follows that if we pick a random vertex u independent from the choice of t, then the probability that L falls in this tree TW up arrow tends to 0 as n tends to infinity. Okay, so what's that saying? It's saying if we take a large random tree, we pick a random vertex W and look at its subtree, and then we look at where the smallest labeled leaf happens to sit. The odds that smallest labeled leaf actually falls in that random subtree is very low. Okay, so let's take a 3-minute break, and I'm happy to answer questions in the chat. In the meantime, I see a question from Suvadeep. Does this exercise imply some local weak convergence to some Galton-Watson tree with Borel distribution as the offspring distribution? Good question. So it's in fact the total size of the tree that's Borel distributed, not the number of children. So we did, you might recall from last class, we saw that the degree of a typical node is asymptotically Poisson, okay? And so if the degree of a typical node is asymptotically Poisson, and the size of this typical tree is, we're saying is asymptotically Borel, that suggests some connection between the Borel distribution and Poisson-Galton-Watson tree, or Poisson branching processes. Indeed, there is a connection there. So the Borel distribution is the distribution of the total number of individuals in a critical Poisson branching process. So again, things will develop. Will likely come to later in the lectures. Question in the chat: when you take a root, say V, the subtree is only the upward vertices, all the subgraph. I'm not sure I understand the question exactly, but so I'm saying, you know, if you, I'll erase this in a second. Let me draw a picture. Right, so in this tree, which has root 2, then the tree, this is the tree T, then the tree T6 up arrow would be this, this tree here. So it's everything, if you like, it's all the vertices with the property that if you go from that vertex along the path down to the root, then you have to pass through vertex 6. So it's vertex 6 plus all its descendants. Okay, another nice question in the chat. So what does it mean by saying the size stays order 1? So another way of saying this is that if I look at so I should really give myself a, to say that I need to make the dependency on n clear. So we wrote T1 up arrow, say, for the subtree, the subtree rooted at vertex 1. But let me write brackets n to indicate that that's inside of a tree with n total vertices. Okay, then the statement that this size stays order 1 is sort of equivalent to saying that these random variables, that this collection of random variables as n varies, is a tight family. Okay, so that's terminology you should know from you know, first rigorous class in probability, and what that means is that if I fix any positive epsilon, there exists some k such that for any one of these random variables, the probability that I guess I want to be taking the size here, probability that the size of that subtree is bigger than k is less than epsilon. Okay, so it's not saying that the sizes are deterministically bounded, but they're stochastically bounded. The probability of them being bigger than something can be made as small as you like. Okay, and then there's a question I'm not sure I can actually answer from Haotian. Can you briefly explain how the fix the tree in step remove factor of argument leads to the uniformness? I think I've used up my my time on questions more. Well, I don't think I understand that question. I'm sorry. I see a question from Manan. If we take the empirical distribution of upward tree sizes, will it almost surely converge weakly to Borel 1 as well? Yes, it will. I mean, you can probably get at that using this exercise, in fact. Yeah, I mean, the fact that a random subtree size is Borel and the subtree sizes are asymptotically independent sort of tells you that. Good. So that sort of continuing on, that sort of takes me to the end of point A, the subtree root at a typical point. And now I'd like to use that to understand the local structure near the root of the whole tree, of a uniformly random tree. Okay. Maybe I feel bad not answering questions in the chat. So maybe at the end of the lecture, Haotian, we can come back to that question. I'll try to answer it then. Okay, so here's what in order to describe the local structure, I need a little bit more notation. So let's take a uniformly random tree, and now I'm actually going to use the bijection in order to understand the local structure near the root. So the bijection, remember, gave us a sequence v1 up to vn minus 1, which was a uniformly random sequence and n to the n minus 1. And that's equivalent to saying that these are independent and uniform on 1 up to n. Okay. And now, so these, remember, so v1 is the root of the tree, and then the early terms in this sequence are building some branch, some line leaving the root v1, right? That's the picture near the root of the tree, v1, v2, v3, and so on. Okay, so I'm interested in the local structure near the root, which means in some sense I'm in part interested in what happens at the start of this sequence. Okay, or at least I'm interested in the sort of the trees that are rooted along that path. So let me give those names. Okay, so I'm going to draw the tree T like this. So here's V1, here's V2, here's V3. Okay, here's V4, and so on. These, with high probability, these are distinct when n is large because they're uniform samples. The probability of seeing two that are the same within a sort of bounded number of steps is quite unlikely. So this picture, even if it isn't always correct, it's sort of a good way to think about the structure of the tree. There's this path going off, and then there are these subtrees hanging off. Okay, and I'll give those subtrees names as well. So let me call this T1 star, and this T2 star, and this T3 star, and this T4 star, and so on. Okay, so maybe to be a little bit more formal about that, so let me actually write this down as a proposition. So I'm going to fix some integer k, and then for I from 1 to k, I'll let Ti star be the subtree, so TVI minus TVI plus 1, up arrow. Okay, so what does that mean? Right, so TV1 up arrow is just the whole tree, right? And I'm saying I want to take the whole tree and then take away everything that's a descendant of vertex 2. So that leaves me with the root and this subtree hanging off. Okay, and then TV2 will be the subtree root of V2 minus everything that's a descendant of V3. So that indeed gives me this sort of subtree hanging off here. So these trees might just consist of a single vertex. They might be large. For now, we don't know anything about them. But as long as sort of V1 up to VK are distinct, then this heuristic picture of what these trees are really is what they look like. They're a tree hanging off that consists of all the things that are not also descendants of the next vertex in this sequence. Okay, so is that definition clear? So I haven't stated the proposition yet, but I need that definition for the statement. So then, given that V1 up to VK plus 1 are all distinct, then these trees, so T1 star up to TK star are independent and uniformly random trees conditional on their sizes and root labels. Okay, so that's the first thing. If I tell you what's in here and what these labels are, then we just have a sequence of independent trees. And moreover, the vector of sizes, T1 star up to TK star, converges in distribution again to a vector of independent Borel one random variables. Okay. So this actually describes the structure near the root vertex in quite some detail, right? It says that provided that that in this sequence here, the first branch is long enough, we have more than k entries before the first repeated entry, then what we see are a bunch of independent random trees, and moreover that the sizes of those trees are asymptotically Borel. Okay, so it's possible, right, that that this condition that these are all distinct fails, and then that means that we start growing a second branch quite quickly, and then the description of these trees becomes sort of less clean. Okay, but that's typically not what happens, and so I sort of don't worry too much about that. Given that is saying conditionally given the event that these are all distinct, that's correct. Okay, so if you like, I'm conditioning on two different things. One is that that these are all distinct, and then the second is maybe a more refined conditioning, which is on the precise no, it's not more refined. I need that these are distinct, and I need to know what the sizes are. Yeah. But really, okay, the statements about, what happens in all of these calculations we're doing is the same. Once I tell you, because I start from a model which is just the uniform distribution over trees, that always projects down to the uniform distribution over subtrees once I give you some data about those subtrees. I always end up with the uniform distribution over the set of possibilities that remains. Okay, so if I tell you, that this tree has a given vertex set and that its root is labeled 12, then it's equally likely to be any tree with that vertex set and root label 12. Okay, the fact that we end up, that the conditioning yields uniform trees in the appropriate classes is not really surprising. That's just a feature of the symmetry of the model. The question is to understand really why we again get Borel distributions out the end here. Okay, so this is what I'm going to focus on. Okay, any questions? Any other questions I can answer before I start explaining why we have this this structure near the root of our large random tree? Do we assume VI is closer to the root compared to VI plus 1? Yeah. So when these are all distinct, then that means that V1 up to Vk plus 1 are all on the first branch leaving the root. There's a path in the tree which goes V1 in that case, V2, all the way up to Vk plus 1. So we don't have to, under this assumption or under this conditioning, Vi is automatically closer to the root than Vi plus 1. Okay. With high probability, there's no repeat before k. That's correct as long as, so here k is fixed and n is tending to infinity. So this is a sort of version of the birthday paradox. So you're saying what's the first repeat in a sequence? That first repeat is asymptotically Rayleigh distributed on a scale of root n. So the first repeat will, you could, maybe I'm answering Lior's and Jost's question at the same time. In some sense, you could push this up to k is little o of root n, and the story I'm telling here would still work in some sense. Yeah, so this conditioning is something that happens with probability 1 minus little o of 1 in particular. So conditioning on, yeah. So if you like, there's two statements here. One is part A is in brown, and it says that under these two bits of conditionings, these trees are independent uniformly random trees. Okay, and the second doesn't have any, doesn't require any conditioning. It's just a statement that that these trees here, so this definition makes sense, on its own. It doesn't require any assumptions. It just says take one subtree, subtract another subtree from it or remove some vertices from it, potentially nothing if this isn't a subtree of this. Okay, you get some subtrees of this random tree, and part B is the statement that their sizes converge jointly to independent Borels. Okay, so I'm not going to focus on proving part A. It's just as I said, it's just because of the sort of symmetry of the model. I'm going to focus on proving part B. Okay, so part A is okay. So to prove this, I'm going to so use a different way of generating a tree, a uniform tree in Tn. And the reason for that is that I want to connect the tree T1 star with a tree T1 up arrow in a different tree. Okay. So the point is that we have this existing theorem which told us that if I look at the subtree rooted at a random node, that's asymptotically Borel distributed. Okay, and now I have a theorem that says a different subtree is asymptotically Borel distributed, and I'm going to prove that by relating the subtree rooted at a random node in one tree with this subtree near the root in another tree. Okay, so in order to connect T1 star with the subtree rooted at a random node in another tree. Okay, and so this is when I say different way of generating a tree, it's fancy words for something very simple, which is just a uniform rerouting. Okay, so I'm going to start from a tree which I'll call T hat, which is a uniformly random tree in Tn. Okay, and then I'll just do the following thing. I'll take a random vertex W, independent of T hat, okay? And then I'll let T be obtained from T hat by rerouting at W. Okay, so the root was already a uniformly random vertex. So if we just resample the vertex that we decide to call the root, we're still just rooting at a uniformly random vertex. So that doesn't change the distribution. Okay, so then T now is again a uniformly random tree from Tn. Okay, but now if I look at the sequence, the nice thing about this is if I look at the sequence V of T, okay, then remember when we apply the bijection, the first term in the sequence is always just the root of the tree. So now we have that V1 is equal to W. Okay. So let's think about what that means for the various subtrees that are involved. Okay, so by the way, I wrote this in the chat during Jean-Christophe's lecture, but if you want to back up in the slides, a useful thing to do is just go to the YouTube live stream, which is linked from the course website, and then you can scroll back in the YouTube video to if there's sort of like notation that you missed that you want to catch or something like that, or if you just want to have more than one slide up at the same time. Okay, so let's see. So we have this tree T hat, and then there's this node W sitting in it somewhere, and then in the tree T, we've taken T hat and just decided to reroute at W, so W becomes the root. Okay, and I'd like to understand what happens to the tree. What's this tree here? This is T hat W up arrow, right? So that's hanging around now somewhere near the root down here. Okay, but what I hope actually is that I can do this drawing like this. I've got the tree. So W is the node V1 for the tree T, and then here's the node V2. Here's the tree T1 star, right? That's everything, all descendants of V1 that are not also descendants of V2. Okay. And now I'd like to say that with high probability, this subtree T1 star is actually equal to the subtree above W in the tree T hat. Okay, and that would that would start to get me toward proving the proposition, because I know that this subtree is asymptotically Borel distributed. So if with high probability it's the same as this subtree, then this subtree is also has Borel size. Okay, so that's the goal. Now, when will it be the case that that this rerouting sends this subtree down to become T1 star? Okay, well, remember this branch here is going along toward the smallest labeled leaf of this tree. Okay, so so we need to think about the smallest labeled leaf, and actually let's start by thinking about that over in the subtree T hat. So let's let L hat be the smallest labeled leaf in T hat. Okay, and so that that could be anywhere in T hat. It could be in here, or it could be somewhere else. But I gave you an exercise just before the break, which said that with high probability, if we pick a random vertex, then the smallest labeled leaf is not in its subtree. Okay, so the typical picture is that the smallest labeled leaf is sitting over here somewhere. We have a path from the root of this tree up to W, and then somewhere there's a branch going off, and the smallest labeled leaf is over here. Okay. So now, when we reroute the tree at W, okay, this means that that the smallest labeled leaf will not be in the tree T, will not be in this subtree. It'll be somewhere out here. Okay. So there's so there's this part of the path heading to W, which is sort of guaranteed to lead to the smallest labeled leaf in T now, assuming that we didn't get unlucky and find the smallest labeled leaf in this subtree. Okay, so if this is the key point with this rerouting construction, is that if L hat is not in the subtree root at W, then T1 star is equal to the subtree root at W in the tree T hat. Okay, and so then what that tells us is that if we want to compute the probability that this subtree T1 star has a fixed value, we can do that basically by computing the probability that this subtree has a fixed value with an error term which is related to the probability that we got unlucky and L fell in this tree. Okay, so let me show you how that computation works. And I know this part was a bit more, a bit hand wavy, but this fact is perfectly rigorous, and we can use it now in a perfectly rigorous computation to bound the probability that that T1 star has a given size. So for any fixed, I'll call it N1, since eventually we're going to have a sequence of these, for any fixed value N1, if we want to compute the probability that the subtree rooted at V1, T1 star, this guy, has size N1. Okay, I can write that as the probability that the subtree has size N1 and an L hat is not in that TW up arrow, plus the probability that T1 star has size N1 and we got unlucky, L hat is in the subtree root at W and T hat. Okay, but now this term is really an error term. It's bounded from above by the probability that we got unlucky and L hat was in TW up arrow. And by the exercise I stated before, that tends to 0. Okay, so that's a negligible error term. And the other term, now we can write when it this fact says that when L hat doesn't fall in this subtree, then studying the size of T1 star and studying the size of that subtree is the same thing. So the first probability is just the probability that that TW up arrow, that the subtree rooted W and T hat has size N1, and L hat is not in this subtree. And now we have this order 1 error. Okay, now we have to do that same sort of extraction of an error term one more time. We can write this probability as the probability that the subtree rooted at W and T hat has size N1 minus the probability that the subtree has size N1, but L hat is in the subtree. Okay, and then we still have this error term. Okay, and now this probability again is bounded by the probability that that we got unlucky and L hat fell in the subtree. So this is another little o1 error term. Okay, so that tells us in sum that the probability we see a given size for that subtree T1 star is the same as the probability that a random node has that size of subtree rooted at it, up to a little o1 error term. Okay, so that tells us that the size at least of T1 star converges in distribution to a Borel. Okay. This is probably a good point for a pause. So the key structure of the proof, up to the computations, was really in this sketch here. You say that when I reroute this tree at a fixed node, then unless this unlikely bad event occurs, then what happens is that the subtree rooted at that node on the left becomes the subtree hanging off of the root, ignoring the first stick of the line breaking bijection on the right, and then this is the math that makes that work. The last step saying that, so once we know that this probability is the same as this probability plus little o of 1, well, we already that says that if this sequence of random variables converges in distribution, then this one must also converge in distribution and have the same limit. And we did indeed already show that these ones converge to Borel. So then this sequence as n tends to infinity also converges to Borel. Okay. I'm keeping my eye on chat for questions. I'm happy to. So that's a good question. Why do we need L not in the subtree of W to have that identity? Okay, so let me draw the picture again, right? So I'll draw it a bit bigger so we can see what's going on. Here's W. Now imagine that imagine that label 1 for that 1 is a leaf, and so vertex 1 is sitting somewhere in here. Okay, so then that's in this picture L is equal to 1. Okay. Now what's going to happen in the bijection when we reroute at W? Well, the first thing that the bijection does is lists all of the labels on the path from W to the smallest labeled leaf. Okay, so the path that it's going to the labels that it's going to list are going to go, W is still V1. Now V2 will be the next vertex on this path, V3, and so on, heading over to W. Okay, so when we in this picture, when we reroute at W and take the subtree T1 star, then will consist of all descendants of W in the rerouted tree that are not descendants of V2. So that means that the tree we remove will be this subtree here. This is the part that'll get thrown away, and T1 star will be all this part outside. Okay, so that's the thing that goes wrong if if the smallest labeled leaf happens to fall in this subtree. It's that the first, in the line breaking construction, the first line, the first branch heads toward the smallest labeled leaf. And for this picture to be valid, that line had better not be heading into the subtree that we're trying to extract. It had better be heading away from the subtree that we're trying to extract. Yeah. So each tree is, remember, a tree is just a connected acyclic graph with a particular vertex that's called the root. So reroot just means choose a different vertex to call the root. So, you know, if I think of the tree as having a vertex set and an edge set, and then a root vertex row, then, you know, I'm taking this the new tree. So if that was t hat, then the new tree t is same vertex set, same edge set, but now the root is, in this construction, the vertex w. Okay, so some other things change, if you like, when I reroute, in the sense that, you know, when I talk about number of children, that depends on, that's, the children are relative to a given root vertex. So that number changes depending on whether or not the vertex is the root. And who are your children, which is your set of children depends on the location of the root in the tree. Okay, so just to finish up, I'm gonna remember, so we proved the first, we proved that the first coordinate of this distributional convergence holds, okay? And so now I'd like to get at the other coordinates. And basically, the argument is the following. It says, well, let's just ignore the first subtree and apply induction to the remaining subtrees, okay? And maybe that's enough for you, and if it is, then you can go to sleep for the next 10 minutes. But if you want to see it, then that's what I'm going to do. So now let's. So if you like, this proves the result when k is equal to 1. Okay, so for larger k, we'll let's write n prime for n minus the size of t1 star. Okay, and I'll write t prime for the tree t v2 up arrow. Okay, right. So that's right. So that's always a way I can decompose the tree t. So here's t1 star, and here's tv2 up arrow. It's everything over here. Okay, if v2, if I'm right, it's possible with probability 1 over n, I'm unlucky and v2 equals v1. Okay, and if that happens, then tv2 up arrow is the whole tree, and tv1 star, which is you know, tv1 up arrow minus tv2 up arrow, is just empty. But this is the typical picture. Okay, and now okay, so what I'd like to do to prove the distribution, the convergence for larger k, is think of proving the convergence of the last k minus 1 coordinates in t prime. I already know that this subtree is Borel distributed, so I'm going to apply the bijection to the tree t prime. Okay, and that'll give me a sequence v1 prime up to vn minus 1 prime. Okay, and now so what does the start of this sequence look like? Okay, well, you know, in the tree T, we had this branch which went v1, v2, going up here to some vk, so on until we reach the first leaf. Okay, and as long as as long as those first k or k plus 1 values are all distinct, so if v1 up to vk are all distinct, then the sequence heading to the smallest leaf over here will just be this same sequence, except starting from v2 instead of v1. Okay, so then v1 prime up to vk minus 1 prime will just be equal to v2 up to vk. Okay, and so we can say a bit more than that, in fact, right? If we think about the subtrees hanging off of this path, well, they're exactly the same in whether those subtrees are the same whether we think of them as subtrees of the whole tree T or just of the smaller tree T prime. It's just that in the bijection, the index of their root is shifted by 1 because this is the new root. So this is v1 prime, right? And vk is vk minus 1 prime, and so on. Okay, and so that that tells me that, in fact, I have something slightly more than this. So more strongly, if I look at the subtrees T star 2 up to T star K, okay, then those are, if you like, T prime. So I apologize for the notation. T prime star 1 up to T prime star K minus 1. Okay, so that's just saying that the subtrees in this tree T prime hanging off of this path are the same as the subtrees hanging off of the path in T, just with indices shifted by 1. Okay, and so so then if I ask about what happens, so if we imagine that this subtree here had some fixed size n1, okay, and we let n tend to infinity, and so that also means that the size of n prime, which is n minus n1, tends to infinity. Okay, then so I said that all this happens provided that v1 up to vk are all distinct. So I'm going to want to condition on that event. Let me call this event E. Okay, then we'll have that the probability that we see some particular sizes for the subtrees v2 up to vk, or sorry, I was just calling them 2 up to k star. So the probability that I see particular sizes n2 up to nk, given that that first tree has size n1, okay, the difference between that and the probability that in the tree T prime, the corresponding subtrees, the prime star I feel bad about, but oh well. The probability that the subtrees in T prime have those sizes n2 up to nk. Okay, how can we bound the, I still want, given that that first tree had size n1. Okay, how can we bound the difference between those two events? Well, we said that these two vectors are the same unless unless this event E fails, right? So as long as v1 up to vk are all distinct, then these two vectors have the same value. And so the only way they can have different values is if there's a repetition among the first k terms. Okay, and so the difference between these probabilities is at most the probability that there's the conditional probability that there's a repetition in those terms, given that that first tree had size n1. Okay, but we know that that first size was asymptotically Borel distributed. So this converges to the probability that a Borel one random variable has size n1, so that's some positive value. And on the other hand, the probability that there's a repetition among k uniform samples from a large set tends to 0. Okay, and so that means, the probability of E complement tends to 0. That's the probability of the repetition. Okay, so this probability tends to 0. This one's positive, so that means the conditional probability also tends to 0. Okay, so what does this computation do? It says that for computing the probability that we see given k minus 1 given subtree sizes in this tree, we can really just think of the probability of seeing k minus 1 given subtree sizes in a uniform tree of a slightly smaller size. Okay, so that's the latter probability, and that we like because now we can just apply induction. So since this size of the tree T prime is tending to infinity, then by induction, we have that that the sizes of so T1 prime star up to T k minus 1 prime star converge in distribution to so independent Borels, but let me call them B2 up to BK. And that's true even given that the size of T, T1 star is equal to K, is equal to N1. Okay, because we compared these probabilities even under the conditioning on a fixed size for that first tree. Okay, and so now because that holds, whatever that size is, okay, that means that that first coordinate, the size of the first subtree, is asymptotically independent of the next subtrees. Okay, so so because this holds, whatever the value of n1, it then follows that so all of those subtree sizes converge jointly. Independent Borels. Okay. So so that's so what does that establish? We said that if we look at the structure of subtrees near the root of a random tree, we decompose that by thinking about this branch heading toward the smallest labeled leaf, and then off of that branch, what we see asymptotically are independent uniform trees whose sizes are independent Borels. Okay, so that structure was described. So this local structure of IID trees along an infinite backbone holds in quite a bit more generality. It was worked out for various models of trees by Grimmett and Kennedy and Keston at various points. So you get, I described the structure for uniform trees, but in fact it holds for, in quite some generality, for critical branching processes conditioned to be large. And then what you see is a sort of a unique infinite path with independent critical branching processes hanging off it as the local structure near the root. Okay, I want to, even though I'm essentially out of time, I want to tell you a slight generalization of that story, not in any great detail, just to tell you what kind of to point you in the direction of the story. So this local limit behavior, actually, there's a slightly more general thing that can happen when you move to the setting of simply generated trees, or more or less equivalently, if you think about subcritical branching processes conditioned to be large, rather than just critical branching processes conditioned to be large. So this was worked out by Svante Janssen in a probability surveys paper in 2012. Okay, and so I'll just tell you quickly what simply generated trees are. So they're so these are trees which are again rooted. They're not labeled, but they have a planar structure. So each vertex has some number of children that are ordered left to right. Okay, so this in this model of tree, these two trees would be different, even though there's sort of a graph isomorphism between them. In this tree, it's the first node that has the first child of the root that has two children. And in this tree, it's the second child of the root that has two children. So these two trees are distinct in the simply generated tree model. Okay, and but then the way that you add randomness to this picture is very simple. You just fix a vector W of non-negative weights with W not positive. Okay, and then to a rooted tree T, you assign weight, which I'll call WT, and it's just given by the product over vertices of the tree of the weight in the sequence that corresponds to the number of children of V and T. Okay, so so if these weights are a probability distribution, then this really corresponds to a branching process. But the model is more general than branching processes. And then we define T and W to be the random element. So a random tree with distribution given by saying that the probability that T and W is T is proportional to its weight. So we just pick a tree with pick a tree with n vertices, but insist that the total number of vertices is n. Okay, so that's some slightly different model of random trees from the ones I've already introduced. If you can imagine taking all weights 1, and then you get some sort of uniform distribution on this class of trees. You could have the weights increasing very quickly, and then you'd strongly prefer trees with very large degrees. But because they're trees, you always have to have leaves, and so that's why this W0 has to be positive. Okay, so when you look at large simply generated trees of this kind, there's two possibilities for local structure. Okay, and one is the picture we just sort of derived, which is IID trees along an infinite backbone. So IID finite trees along a path. And the second picture is a bit different. You again have IID finite trees, but what happens is that you have a geometric length path And at the end of that path, there's explosion. So you have a single node of infinite degree at the end of which you have some more IID finite trees. Okay, so all of these trees, both along the path and at the explosion at the end, all have the same distribution. Okay, so this is a second sort of local phenomenon that can occur for certain models of random trees. And I won't go much into the details of that, but I thought it was worth mentioning because I talked about universality. And this story that I told up here for uniformly random trees is a quite general story. And you might call it sort of, say, in some sense, gives the universal limiting picture, but that's not literally true. There is this other kind of local limit that's possible near the root of large random trees. And that's been developed for simply generated trees. If you're interested, I will refer you to this paper of Janssen for more. Okay, sorry for going a little over time. Those of you who are still here, thank you. Those of you who are MSRI participants who are interested or who are planning to do the group exercises, please do sign into Sococo at the hour, so 25 minutes from now. And for the rest of you, I'll see you on Thursday. Yeah, I'll stick around for questions as well, of course. And I see one in the chat. Is there any intuition behind why this explosion happens? Yeah, so roughly the idea is that so in certain models of trees, if the question is, you know, what when you give trees probabilities proportional to these weights, what sort of degrees do you get out of that? So in some sense, what's the easiest in this probability here? What's the easiest way to build a large tree? What large trees have the most weight? And it turns out that for certain classes of weights, the easiest way to make a tree large is just to make one vertex that has huge degree, okay? And then let most of the other degrees be small. And when that happens, when there's a single vertex of huge degree, well, in the limit that can lead to a sort of a vertex of infinite degree, and then a bunch of small degrees and small trees hanging off. I think that's about as much intuition as I can give at this point in the course. I might be able to give a little more later as we go along. Leo says, can you scroll back down to the next slide? Do you mean this one or in the other direction? Great.